So what you do is that you construct a matrix with the elements. So in this case, processor number 1 wants to send 60 elements to processor number 2. And it depends on which metric you want to minimize. So if you want to minimize the maximum data mode from one processor, then you can construct the graph given the matrix here, and then you weight the edges with some penalty function, and then you simply solve maximum cardinality problem, something that you select some edge that will lower this data movement. What we do is that we try to minimize the total volume of data moved. So then this will become a nice graph matching problem, bipartite graph, weighted with the entries in the matrix, and then we can simply solve it. And everybody knows it is fairly expensive. And the number of edges in this graph is, in the worst case, the number of processors squared. So we use a quite efficient algorithm that has this runtime, the number of edges. So we simply sort the matrix, linearize the matrix and sort the entries, and then simply picks the largest entry that isn't assigned to any partition yet. Okay, so now let's see if we can get the movie working. So this is fairly recent ongoing work. I haven't really tuned the load balancer for the revolve refinement yet. So what this means, can we make this? Okay, so this we can do it once more, because this was given that we start to refine in the left corner. The coloring here is the processor ID. And for each refinement, I do load balancing and repartitioning and redistributing everything. So you see that in the beginning, it doesn't function so good. But when we have, in the end, when we have almost all the refinements in one place and a lot of elements, then it doesn't move the too many elements between, it minimizes the data movement. And it also works in 3D. So now it's going to start to refine in this corner. And it actually works better in 3D than in 2D. It didn't work at all. Now it works. Okay, speed up. So we have done some tests on a pretty small blue gene. It's only 1024 node, it's one rack, so it's probably the cheapest one you can buy. However, 2048 processors if you run in virtual mode, but then you only get half the memory, that means 512 megabytes. So we run this in co-processing mode, where one of the processors handles part of the communication. And this has been tested with a flow solver from Unicorn. And also have a nice picture. So this is the refinement. And the baseline here is 32 processors, because that's the smallest amount of processor you can allocate on the blue gene. You can run it on less number, but you have to allocate 32. And we have this memory problem that you only have 1 gigabyte per node, so we can't really fit the problem in less nodes. Anyway, linear speed up to 128 processors. Then it starts to flatten out. But should keep in mind that mesh refinement is a local problem, so this is probably pretty good, or not perfect, but it's okay. And if you break down the results here, you see that the load balancer actually scales very good. Redistribution from the load balancing also scales good. Repartitioning with parameters actually doesn't scale so good. It seems to perform best up to 128, and then it goes down. But that's not my code, so it's not my problem. Or it's my problem, but I can't complain. I can complain all the bad results on that. Okay, so this is basically what I had after my master thesis. linear speed up almost up to 512 processors. Yeah, perfectly. This was with GNU compilers, and actually a pretty small test case, 500,000 vertices. But still, nice results. So now when I have cleaned up the code, it actually compiles with the IBM compilers. So we scale it up. And now it's terrible. 1 million vertices instead. And we have this really fancy optimization. So it takes 2 hours to compile Dolphin. But then we get dual FBU code, single instruction, multiple data, and all the fancy stuff. However, scaling, not so good anymore. So now we can question what went wrong. Yes. Profiling, didn't say so much. Assemble cells, oh, that wasn't so unexpected. Interpolate, no. Matrix insertion, I mean, it's the usual suspect. The drag form, we couldn't really compile it with full optimization because I started in the morning and after lunch when it had consumed 4 gigabytes of memory, I killed it, so I was a bit lazy. And the MPI tracing didn't work. But I can probably blame that on a broken node card in the blue gene, so that's the reason for these results. No. Okay, but some possible serious explanation here is that the IBM can compile the tabulate tensor, for example, pretty good. And it compiles much faster code than the GNU compilers. Actually, this data point here has the same runtime as this data point here. So you can basically assemble twice the amount of vertices. But another thing here is the communication. We don't have any communication hotspot, even though I didn't get the MPI tracing, I know that. But on the blue gene, compared to a boring pile of PC cluster when you have this InfiniBand interconnect in switches and the switches are connected in a fat tree, it's basically the same cost to communicate to any processor. But on the blue gene, you have this 3-dimensional torus with XYZ connections. So it seems to be important that you talk to only the neighbors, the physical neighbors. So we probably have to do some work on minimizing the communication. And that means remap the processor so that you talk to the neighbors only. And another thing here is that the problem size is also probably too small. But we cannot increase this. This is the maximum amount of vertices I can fit on 32 processors. I don't want to get into the questionable business of scaling performance results.
These are strong scaling results and not weak scaling?
You mean the same amount of vertices?
Right, same number of vertices, yes, rather than same number of vertices per processor.
No, yes, this is same mesh for all the cases. So this is the true thing.
Did you do a weak scaling also?
Why? That's cheating.
Well, it's a different method.
I'm honest here. I'm showing you the honest picture here. So.
Yeah, no. I mean, you can do both versions. One of them will tell you whether or not you screwed up the communication. I mean, weak scaling at least will tell you that.
I'm pretty sure that I screwed up the communication with this, not optimizing for the network topology. Sure. Because in the profiling, I had some BGL, C, something strange. So that's probably the routing. And okay, so what do we know? The blue gene is absolutely user-unfriendly to work with. We get 1 core dump per each processor, and they are in ASCII format. That's basically it. However, something from the never-ending to-do list: reduce the memory footprint, modify the load balancer so that we add and remove processors from the problem. So if we start with a fairly coarse mesh on 32 processors, when we refine, we're going to add more processors dynamically. It seems to work on paper, that I just need some time to implement it. Checkpoint restart, that should be needed for the serial Dolphin as well, I think. And I extra have some bug in the Rivara refinement, but it only affects unstructured meshes, so I'm going to use structured from now on. Okay, So since I didn't have this good performance, I found this nice quote from Supercomputing 98, I think. It's from the 12 ways to fool the mess about parallel performance something. So I'm going to end with a nice picture and hope you don't talk about performance.